Ralph Ferraro here. Welcome to our seminar series. I'll go real quick here. So Neil's professor of chemistry at Carnegie Mellon University. He's a physics degree from Brown University, PhD in meteorology from MIT. And he does a lot of work with atmospheric chemistry, and on aerosols, and he is fellow of the AGU and also American Association for Aerosol Research. He's won a lot of awards, and he's involved with a lot of journals and other important things. So I'm just going to turn it over to him, and be interested to hear what he has to say.
All right. Well, thanks very much for the introduction, the invitation, and bearing with me with my little technical difficulties there. So with any luck, this will go fine. And I'll move right along. As always, I have a little more to cover than I probably should, but I think we can, well, I'll stop when we're supposed to stop in any event. There's a few stopping points here. So in fact, I'm literally not quite fresh off the plane. I'm not quite fresh, but back from a meeting in Vienna where we were talking about some of the topics today. So this is all, as is always the case, this represents the work of a number of outstanding doctoral students, both in my own group, who are listed here: Meredith Shervis, Ching Yu, Mingyi Wang, Brandon Lopez, Jenna DeVivo. Meredith is currently a postdoc with Manabu Shiraiwa. Ching is a research scientist at NCAR. Mingyi just started a faculty position at the University of Chicago, and Brandon and Jenna are still in the group. And this is mostly we'll be talking about research associated with this consortium called CLOUD, which I'll talk a little bit more about later, in which, as I say, I was just at the data meeting for. So let's see if we can make slides go. That's them: Meredith, Ching, Mingyi, Jenna, and Brandon. First off, I know not every one of you is an aerosol person, so I will just glide through a couple reasons why we actually care about fine particles in the atmosphere. I don't use pointers a lot, but can you see my little hand? I don't hear a yes or a no.
Yes, we can. Sorry, I thought I was.
Okay.
That's great.
Cool. And let me just poke on the chat here and boop that and put this over here so I can keep track of that. Okay. This is from a meta study published by Seard and Pope quite a few years ago now, but I think it's one of the more dramatic illustrations of just how striking the health effects associations are with fine particles. So on the x-axis here, you have the fine particle mass. PM2.5 is particles smaller than 2.5 microns in diameter. And we measured those in micrograms per cubic meter, which, by the way, is parts per billion by mass, because the cubic meter weighs about a kilogram. That's important. Remember that a little bit later. And the y-axis is life expectancy. These are 50 metropolitan areas across the United States in 1980, as you see. And I would have put the little, three inverted star symbol of the steel industry and the Pittsburgh Stillers on that golden colored circle there, but you get the drift. In 1980, Pittsburgh was still the still city. The steel industry hadn't quite collapsed. I'm from Pittsburgh, so I get to say still, and it was quite polluted. It wasn't hell with a lid off anymore, but we had about 30 micrograms per cubic meter, and we had among the lower life expectancies in the continental United States. And you see that association line. As it gets cleaner, people live longer. And then if we go to 2000, so 20 years later, the Clean Air Act had started to take effect, and returning to those 50 municipal areas, people were living a couple years longer. There were no longer any areas with more than 20 micrograms per cubic meter of fine particulate matter. A number had poked in between this 5 to 10 microgram per cubic meter range. These two kind of magenta colored vertical dashed lines are the National Ambient Air Quality Standards. I should have another one in here because we're going down to 8. These are we started at 15 micrograms down to 12 microgram per cubic meter. Actually, all of these standards were formally promulgated after 2000. So this is a side benefit of catalytic converters and sulfur SO2 scrubbers and such from other aspects of the Clean Air Act. But air had gotten a lot cleaner, people were living longer, and fully 20% of that improvement in life expectancy is directly attributable to the cleanup from reduced air pollution. It is an incredibly big deal. Now, still, there's about 50 to 100,000, it says 50 here, but lives lost per year due to air pollution in the United States. But the Clean Air Act is saving at least 50,000 lives per year, depending on how you count it. We have an environmental economist, Nick Muller at CMU, who is folding in avoided environmental damages into basically GDP. And those avoided damages can be worth large fractions of a point in GDP, which is an incredibly big deal. This is over the past 40 years ago. If you actually fold the benefits of improvements to air pollution and not just count the cost of putting catalytic converters on your cars, it's an incredibly big deal. So we care about particles for health effects. And of course, we also care about particles because of climate. And this is just one of many pictures off the west coast of the United States, which you can kind of make out on the right-hand edge here. There's 1,000 kilometers or so taken from the space shuttle, and it's a photograph of the stratus decks that pervade the eastern limits of most major ocean basins. In this case, the eastern Pacific Ocean. And these long sort of swooshes have nothing to do with Nike, even though the headquarters is over there somewhere to the right. Those are long trails of ship tracks. They're also not smoke. They're plumes of transformed, these are actually open cell stratus clouds that have got switched to a sort of a closed cell. The circulation of the cells is reversed, and they cloud up and they turn white. And that kind of contrast of white over dark ocean is a change in planetary albedo. And these tracks, as I say, they're not smoke, and they're up to 1,000 kilometers long, and they're because of specifically of the sulfur emissions from the bunker fuel that those freighters have out in the open ocean. Actually, banning sulfur from bunker fuel was an interesting discussion that we might have in question and answer. But so that is just one of the more vivid illustrations of aerosol indirect effects on cloud and aerosol cloud interactions, which is reason number 2 that we care about aerosols. Something on order of a third, but it's a highly uncertain third of long-lived climate forcing is masked by the aerosol cloud effects, which happen to be killing 7 million people around the planet every year. And so with the removal of that masking, we'll reveal a significantly greater amount of aerosol forcing. And also the way that aerosol forcing, climate forcing will proceed along different decarbonization shared socioeconomic pathways is not at all certain. So it's not just our ability to understand climate forcing retrospectively from the pre-industrial that's uncertain, though that's very uncertain, but also our ability to forecast how aerosol particle number will influence aerosol cloud interactions in the future. That is just a critical need, and that's what we're about. So to give you a sense of why we're about that, this is a sort of a cartoon illustrating a budget for cloud condensation nuclei that are responsible for those ship tracks and all the other aerosol cloud interactions averaged over the globe. And this is work from my colleague Peter Adams and his student Dan Westerveld, now from about almost more than a decade ago. But this is just averaged over the globe, actually in a model with pretty good aerosol. Well, at the 10 years ago, state-of-the-art aerosol codes in it. And this shows you the flux of particles into and out of various modes that we care about for aerosols. And so this is a sort of a general diameter axis on the x-axis, and then a distribution on the y. And this dashed vertical at 100 nanometers is very roughly speaking the division between ultrafine particles and cloud condensation nuclei. In order to play in that aerosol cloud activation game, particles have to have enough moles of solute to be able to suppress the vapor pressure of water and thus enable cloud activation. Of course, that varies with not just composition, but updraft velocities and such. So anywhere between 50 and 100 nanometers or more, depending on those will be exactly where you kind of draw that cut. But here we've nicely put a minimum there anyway, so it doesn't matter very much. But the key is these red arrows here. So the bottom line message here is that almost all CCN grew up to be CCN. They grew up from much smaller particles that then undergo condensational growth to get big enough to actually act as CCN. Direct emissions of CCN on a global average are very small, tiny red arrow there compared to the growth. Now, if we look on the left-hand side, the origin of most of those ultrafine particles is nucleation. But there's also emissions from combustion around 10 or 20 nanometers and everything else, which is the arrow in the lower left. In the nucleation aspect, you see that there's maybe 10,000 particles per cubic centimeter per day on average nucleated around the planet, but only 100 or 200 managed to get from 1 nanometer to 10 nanometers. So there's an incredible loss along just the beginnings of that curve. And further, only a fraction of the particles that get to 10 nanometers make it to be cloud condensation nuclei. The reason is shown here. Small particles are very jittery. They have high Brownian motion, high diffusivity, and they have a strong tendency to bump into bigger particles, and bigger particles just eat them. So that coagulational loss is responsible for the removal of most fine particles. As they get bigger, like everything, they settle down, they slow down, and they become less diffusive, and consequently their coagulational loss gets smaller and smaller and smaller. And so that's going to be illustrated here as this particle grows from a cluster up through to about 10 nanometers with this giant CCN hovering over the top of it. And typical coagulational loss rates are shown in these arrows. So what we call the survival probability of those particles is exponentially related to the growth rate as it races across this, what I call valley of death, between a couple nanometers and 10 nanometers versus essentially the surface area of these large particles, or the collision frequency, the condensation sink to these large particles. The bigger the condensation sink, the slower the growth rate, the survival probability decreases exponentially. Correspondingly, faster growth rates, smaller condensation sinks, and the survival probability can get higher. So we care about the formation of stable clusters and then their nucleation into particles, but we also care about their growth as they try to get across to be at least 10 nanometers in size, and then ultimately up toward 100 nanometers or so. And that's what essentially everything I'll be talking about today relates to. Okay, now let me back up one step here. Just to, I use the International Standard Aerosol Mass Spectrometer color markings here. Particles in the atmosphere consist loosely of inorganic salts, a certain amount of other stuff that some people in the audience surely care about a lot, so I apologize for insulting them that way. But inorganic salts, ammonium sulfate, ammonium nitrate, sodium chloride over the ocean, some interesting other chlorine species, and then a whole host of organic material. The inorganic salts here are represented as red. The green stuff is organic. And the very large majority of the condensational growth taking place just about anywhere in the atmosphere consists of growth from organic compounds, so the green stuff. And we've also found that green organic compounds, as I'll be talking about, can play in particle formation itself. And so it's the condensation of organic stuff that we really care about. So let's do a little primer on how we think about organics and volatility, and then I'll show you some results on this. So we need those organic compounds to stick to particles and make them grow. So stickiness is the opposite of volatility. And so I think about volatility. So we got an x-axis here with things being more volatile on the right, less volatile on the left. Pretty straightforward, eh? And some very volatile things, from my point of view, are compounds like toluene in the upper right here. So aromatics associated with human activity and fossil fuels for the most part. And then fun organic compounds like alpha-pinene shown here, monoterpenes, isoprenoids, sesquiterpenes, as we'll see, that are emitted in copious quantities from trees and other biological activity. So those are the two classes of compounds we care about. And they are very volatile by my standards, as I'll go into a little bit more later. But these things, of course, undergo atmospheric chemistry. As an atmospheric chemist, that's what I think about, is the oxidation of hydrocarbons and organic compounds in the atmosphere. Sometimes that oxidation makes the volatility get smaller. Now, the end product of that oxidation, if it's carried to completion, is carbon dioxide, which is extremely volatile stuff. And so it's intermediate species on the oxidation sequence of these hydrocarbons. When you add polar functional groups, the volatility goes downward. And we can think about some, so we'll put a yield axis on this, and we can think about some fraction of those oxidation products that have a low enough volatility that they will actually stick to particles and make them grow, or even a tinier fraction that might have a low enough volatility that they can actually stick to other individual molecules and form molecular clusters and start the process of nucleating particles. So it's essentially those, those fractions, the yields of the species that can nucleate and the species that condense that we care about in this incredibly rich oxidation chemistry of hydrocarbons. So a few years back, almost 20 years back, we started to develop this thing I call a volatility basis set. And the general idea here is that the saturation concentration or volatility is the property I care about the most when I'm trying to think about if all of this soup of organic material is going to condense when it runs into a particle. And I sometimes know specifically what those molecules are, sometimes I don't. And so rather than try to carry surrogate molecules around or other things, I figured that I should just focus on that principal x-axis of vapor pressure, and then also put in something having to do with chemistry, and that's going to be a y-axis here, where we might think about the kind of the oxidation state of carbon or roughly the oxygen to carbon ratios. Either of those work reasonably well. And so on the bottom, we have an O to C ratio on the right-hand side here of 0, and we get above 1 for many of the compounds that we encounter in the atmosphere. And this x-axis is logarithmic, and it spans a huge, huge, huge range. 10 to the 9 micrograms per cubic meter on the right-hand side, a billion micrograms per cubic meter, 1 microgram per cubic meter. These are log values, right? So the 0 here is a microgram per cubic meter. And as you'll see later, I go way below 10 to the minus 5 these days. This is an old slide. And there's some, the colors in these indications, these acronyms on top are just broad classes that have useful attributes and characteristics, which is how we kind of separate things out here these days. So for starters, let's just get rid of that chemistry axis, and we'll just focus on the volatility axis. And again, this is in saturation concentration units of micrograms per cubic meter. Those are the same units that we measure fine particle mass in, and that's not an accident. So way on the left, we have compounds in gray that I call the extremely low volatility organic carbon. Technically, these ranges are defined by saturation concentration, but I'm not going to go there in this talk. So the ELVOCs are things which, if it's a molecule, if it finds itself in the gas phase, it doesn't really have any business there. It got generated by chemistry in the gas phase. And if it hits any surface, it will stick, full stop. There's no return from that surface. So these are no matter how small that particle is either. The next range up, and it spans 3 or so orders of magnitude in vapor pressure and saturation concentration, are compounds I call low volatility organics. They're more volatile than extremely low volatility organics. And they also tend to stick to particles. They don't really want to be in the gas phase, but their vapor pressure does matter. And so sometimes the little residue that's in the gas phase matters because it can get oxidized, but more commonly, things can get in the way of these condensing onto particles. Most notably, if the particles are extremely small, they won't stick as well. So there's a little bit of a vapor pressure that matters a little bit. And then we hit this, we hit this green range here, which are the semi-volatile organic compounds. And they have significant fluxes in both directions. They have activities in the gas phase, saturation ratios that are maybe equal to or less than 1, and they'll have fractions in the similar activities in the particle phase. They tend toward equilibrium. And the thing to really note here is what I mean by semi-volatile. So typical semi-volatile organics, these are things that are, say, 50-50 partition between the condensed phase and the gas phase at equilibrium in the atmosphere. Paraffin, C25 pentacosane, i.e. candle wax, would be a semi-volatile in my book. Levoglucosan, a tracer of biomass burning that's used by lots of people, is mostly in the gas phase in the atmosphere. It's a semi-volatile organic compound. Things that you would, as a chemist, call semi-volatile are way off to the right in this space. It's to be, remember, 1 microgram per cubic meter is a part per billion by mass. And that actually means that you need a vapor pressure of about 100 parts per trillion, 100 ppt in atmospheres, 10 to the minus 10 atmospheres, to be in this range, to be on just on the left-hand edge of that range. It's an incredibly low vapor pressure. And getting there through oxidation chemistry is a fancy little trick. And that's what we'll talk about next. So here is a typical organic oxidation diagram that you might learn about in an introductory atmospheric chemistry class. And a huge amount of research has gone into this. I credit Roger Atkinson and Janet Airy and Paul Zeman with hundreds and hundreds of outstanding papers articulating all this chemistry. Really starts with Logan et al. And thinking about methane and subsequently do that. So we got an organic compound on top. Something happens to it. It gets attacked by a radical, or ozone maybe oxidizes a double bond. And very quickly you wind up with a peroxy radical here called RO2. Those are the super interesting guys. They got choices. They can react with NO under high NOx conditions. They can react with HO2 under low NOx conditions. If they react with NO, you wind up generating ozone photochemically. You make organonitrates. If they react with HO2, maybe most of the time they make hydroperoxides, which can be photolysed and do other interesting things. Eventually, you bump down to this alkoxy radical, RO step, and those do all kinds of interesting stuff, and eventually make some sort of oxidized intermediate compound. In that process, you may or may not break a carbon-carbon bond and start busting that molecule up into smaller pieces. Again, you're trying to get to carbon dioxide in the end. That was kind of the receive, and there's lots of interesting kinetics in there. But we thought we understood that pretty well. However, a couple things have emerged in the past 10 or even less than 10 years that kind of threw a little bit of a monkey wrench into this simple story. One of them we call autooxidation, and this is not new to chemists, but it's new to peroxy radicals in the atmosphere. And this is behind, if you're a combustion chemist, you've ever heard of QOOH in combustion chemistry, this is what that's about. So what can happen is peroxy radicals can isomerize themselves. That ROO moiety really wants to be an ROOH. That terminal oxygen is a radical, and they can reach across the backbone and abstract a hydrogen from the backbone of that molecule and be happy and make an OOH moiety on the peroxy radical. However, that leaves a carbon center radical, which never sticks around the atmosphere. The carbon is immediately kind of healed by a molecular oxygen. And guess what? That's another RO2. It just happens to have an OOH functionality on it. Well, that RO2 will reach over, grab another hydrogen, make another OOH, which will then add another oxygen, molecular oxygen, to make another RO2 radical. And that can go on very quickly and through multiple isomerizations, multiple hydrogen atom transfers, and you can get molecules that look like Colossus on the right-hand side there. Incredible. And that can happen in seconds to hundreds of seconds, depending on temperature and other conditions. So that
I think we lost you, Neil, unless it was just me.
No, we lost audio.
Oh, we can't hear you anymore, Neil.
Yeah, this is Ross too. We should like wave. I'm putting my thing on.
Oh, here. I don't know if it sounds like he's gonna.
Neil?
Hold on, I have a cell phone number. I can give him a call. See if maybe he can. Oh, he's on a rush.
It's just going on and on for you.
Oh no. One sec. I'm gonna call him, see if maybe I can get his attention.
Ross can tell us what he's saying. He's
Oh, I can tell you a lot about Neil. We played intramural basketball together. You might have to, bribe me in some way. No, he's a great guy. Oh,
I can tell you about his father.
yeah, Tom.
He's
No
not.
response. I'm gonna try to raise my
Yeah,
hand.
he has our pictures off, obviously, which I
Yeah.
would too. I mean, because right, he don't want to see me drinking coffee.
Oh gosh, I don't know how to get him to.
He just got into the really interesting stuff too. I sent him a text. I don't know. Do you have his cell phone number?
I did. I just called him. Actually, it's probably his office number that I have. I don't have his cell phone.
Yeah, I know Neil pretty well, but not well enough to have a cell phone.
Oh, I feel so bad. He's
You could
Um,
you could
what
cut it
can we
off and you'll
do?
have to come back.
Oh, you
I did a
can
good
kill the
idea.
screen share.
Let me
You
take
can
it from
skill.
him.
Can the
Yeah.
administrator? Yeah.
Oh, he got it. Neil, yeah, we can't hear you. That's why I took your screen.
That was good.
Okay, good. He's still talking. Oh no.
No,
Well,
he's in the chat, so he's got it this time.
Oh, okay.
he figured it out.
So Neil, we stopped hearing you about 2 minutes ago.
Yeah, maybe he can't hear us either.
Back?
Oh, can you hear us?
Yes.
Okay, we lost you just about at the point you were talking about how to make those massive backbone ketones that have extremely low volatility. So if you go back
Gotcha.
minutes,
This guy. So was did you hear me talking
Yeah.
about auto oxidation? Okay.
yeah, just after that is where
right.
we lost you.
Very good. Okay. Sorry about that. Man, this has been a technically challenged. So the next step, yes.
It was really good stuff too. We didn't want you to stop.
We do this auto oxidation. I don't know what's going on here. I apologize, but we make these highly oxygenated peroxy radicals through this process of auto oxidation, and then it turns out that as the peroxy radical kinetics are really rich. So one of the nice things about this reaction of RO2s with NO and HO2 is, for the most part, they all have the same rate coefficient. All the reactions are about 10 to the minus 11 cubic centimeter per molecule per second. They're not exactly the same, and they're pretty much temperature independent. And so it's the ratio of NO to HO2 that really matters to whether you call yourself high NO or low NO. And they are, it doesn't matter very much. And that is manifestly not true for RO2 plus RO2 reactions. They span this incredible range, and both in the rate coefficients and the products. So as a very sweeping generalization, as those R groups get more and more functionalized and more oxygenated, two things happen. The rate coefficients go up and they become ultimately gas kinetic. So every collision goes, and the products prefer to make these covalently bound peroxides, ROOR. And so they're very big and they can have exceptionally low vapor pressures. And even though the yields are overall fairly small on the mechanisms, they're very consequential. So that's going to be what I'll talk about next. I'm going to make sure this chat stays open, so you can get in touch with me if we drop out again. Oh, I should very much, let me go backwards here, sorry. One of the colleagues who contributed a lot to understanding this was Astrid Kienler, shown there. Good friend of mine who very tragically died last year from medical complications from anyway, it was just it's a terribly sad thing. And every time I talk about this, I think about Astrid. So the talk and everything I do basically is dedicated to her these days. So now let's put this process and give you some sense. What this volatility basis set thingy that I use is in once we discretize the space, and we have versions of this that we put in chemical transport models. But it's also kind of a blackboard on which I think about how chemistry plays out with respect to these properties that I really care about. And this is an example of that. So this is now placing the oxidation of alpha pinene in this space. And so to orient you a little bit, the alpha pinene is this red square in the lower right-hand corner. And there's some curves that have shown up now. There's two gray curves, one labeled 10, one labeled 20. That's carbon number. So alpha pinene is 10 carbons, C10H16. And so there's roughly the 10 carbon number goes stretching up to the upper left-hand side here. winding up in this new range. There's a new range as well that I'll talk about in a bit called the ULVOCs. You see it's going down to 10 to the minus 15 micrograms per cubic meter. And there's a second gray isopleth here, which is 20 carbons. And that's for those dimers. We call them dimers for the peroxides and other covalently bound products. And then there's a sequence of ever darker green circles here. And those are those peroxy radicals. So what happens is if we think about the reaction of alpha pinene with ozone, after a lot of stuff happens that I really care about a lot, you wind up with the peroxy radical and an OH radical and some other things. But so that's that first light green circle. And then that peroxy radical can start the auto-oxidation game. Some of them can start the auto-oxidation game at a certain rate. It's hydrogen atom transfer, remember? And so they go boopity 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 down roughly along this 10 carbon line. Exactly where they're placed is a whole different story that I'm not going to, I'll just gloss right on over that. And we're still working on understanding exactly where we are in that space. And eventually those radicals are going to resolve themselves into molecules. Like I put a couple up on top here in these darkest greens is a downward facing triangle and a square. The square is basically a C10 peroxide, and the triangle is kind of the average of all kinds of other molecules that can come as these bits and pieces kind of fall apart and resolve themselves into other molecules. So there's a string of products along that 10 carbon line. The green curves are oxygen number. So we've got 4, and they go every 2, 4, 6, 8. There's a 2 that you can barely see, 2, 4, 6, 8, 10, 12, 14, 16, 18 oxygens as we move diagonally from the lower right to the upper left. Now these peroxy radicals can react with each other, and then these diamonds are various of those covalently bound products of the RO2 reactions, and they're going to gather around that C20 curve. We have these same classes I spoke about earlier, ELVOCs, LVOCs, SVOCs, and then we've added in this purple ultra low volatility organic compound bin. And the ultra low volatility organics are the ones that have a low enough vapor pressure that under atmospheric conditions, they will actually tend to stick to each other, at least with some reasonable frequency. If you get far into this ULVOC range and 2 of those molecules interact with each other, then they're never coming back apart. And so in the simplest of terms, they are the nucleators. So I care about the collisions and the yields of those things because they are going to make particles. So as an example, we do implement various chemical mechanisms within this framework. This is some work of Meredith Shervish. And if I look at yields of alpha pinene oxidation with this same x-axis we were just looking at, but now we're just adding up all the products, and the colors on these bars are different pathways basically, and different classes of products. So the light green stuff is most of the carbon, and these are the sorts of secondary organic aerosol products we've been studying for years. But there's this tail going off toward lower volatility of various crimson kinds of colors, with the sort of cherry burgundy color are those covalently bound dimers. And you see that dwindling off into this ultra low volatility organic carbon range. And it's a very thin tail. But if we zoom in on that tail, we see that now the carbon yields along there in this specific model implementation of the chemistry, we're looking at per mil kinds of yields. These are decadal bins in this volatility basis set. So they're very, very low yields, but they matter, as we'll see. But of order per mil, which is kind of scary. So now let's take a jump here, and how am I doing on time? And actually look at some data. So as I said, I just got back from a data meeting from our what we call Cloud Consortium, and every fall we do experiments at CERN on a very large 27 cubic meter, incredibly clean chamber we call Cloud. And this is that's Geneva Airport up to the right. CERN is this triangle in the lower part of the figure here, and that big white circle is the Large Hadron Collider. As drawn on the map, you can't see it on the ground like that, of course. And we live in the proton synchrotron, which was the accelerator that was used in the 60s and 70s. And the proton synchrotron is still used to get the particles moving to high enough energies so they can be put into the superproton synchrotron, which is the bigger circle, which then feeds them into the Large Hadron Collider. So whenever the LHC is on, the proton synchrotron is on, and we can spill off beams once the LHC is full enough. They don't need any more protons, and we can like any beam line. This in our case, we take pions off of the beam line and use those as mimics for cosmic rays. In other words, we use them to make charge. And because we can use this the PS beam to make charge, we can generate ion pairs at rates that span the troposphere. We can let galactic cosmic rays that are just going through the East Hall at CERN generate cosmic rays at surface concentrations, or we can use the beam to get up to upper tropospheric charge generation rates, or we can sweep the chamber clear of particles with a high voltage clearing field and remove all ions and only look at neutral chemistry. And so we're able to have very good control over the ion pair formation rate. The other thing we do is we can vary temperature from about 223 Kelvin and even lower up to 303 or higher Kelvin. So we can span the range of temperatures in the atmosphere as well. So we put every fall we go there, we take a lot of mass spectrometers and particle instruments. Here's our group setting up our iodide chemical ionization mass spectrometer, where we look at particles, we look at gas phase compounds with an ion molecule reactor. We also collect particles on a Teflon filter and then thermally desorb them using temperature program reaction spectroscopy. And using that, we can determine the composition of the particles, and based on the temperature that they desorb at, we can also constrain the vapor pressure of those constituents just using standard temperature program desorption, calibrated with polyethylene glycol to determine the vapor pressures of those products. And that gets us a lot of information. So as an example, this is some products that we observed at Cloud from oxidation of alpha pinene in green on the right, and then also from oxidation of naphthalene in gray on the left. And these are dimer products. So these are products of that association reaction. And this is also, there's lots and lots of evidence that those are actually covalently bound dimers, most of which I don't have time to get into here. But one of the pieces of evidence for that is these things come back off of our filters when we warm them up. And so that they're strong enough so that they can survive the heating to come off the filters. And an interesting thing here is the vapor pressures we see for the monoterpene oxidation products and the naphthalene oxidation products are very, very, very different, as in 7 orders of magnitude in vapor pressure or so. And those two dashed curves going through them are actually two parameterizations that we had produced for the volatility basis set based on what we understood the chemistry to be for the terpenes, which involves a lot of that autooxidation, and for aromatics, which instead involves a lot of OH addition into aromatic rings, and that was actually the original volatility basis set volatility parameterization. And quite comfortingly, those parameterizations are reproduced by the observations of vapor pressure quite well. So this was some work from Ming, published in Environmental Science and Technology a few years ago. So again, the dash curves were actually published before we got these data to put onto this figure. So we're fairly comfortable that we understand the relationship between vapor pressure and functionalization down into incredibly low volatility ranges. But then also, if you're thinking on your feet here, this means that different organic compounds can get distributed differently in this space, even with the same sort of nominal composition. So that's something where if we try to go the other way from ambient observations to volatility, it can make it a little more exciting. So let's look how we're doing here. Quarter of. I'll take about 5 more minutes to run through one story on this, and then just glance by a couple of other results, and you can get a sense for how we're beginning to understand some of the richness of particle formation chemistry in the atmosphere. So this is we look at alpha pinene a lot. It's one of the main monoterpenes emitted in the atmosphere, and it's become sort of a reference compound for a lot of our research. And this figure shows the formation rate that we observe in cloud on the y-axis here, and it's a logarithmic scale, versus the concentration of these ULVOCs in molecules per cubic centimeter here. So back up again. The ULVOCs, remember, this purple range of compounds. If I go even a few more back, these guys, which are way at the end of this tail, that we think are responsible for particle formation. So let's go forward again. So we can measure those directly with mass spectrometers now, and we're measuring them at incredibly low concentrations, right? 10 to the 6, anywhere from 5, 10 to the 5 to 10 to the 5, 10 to the 6 molecules per cubic centimeter. And the colors are different temperatures, ranging from minus 50 C, the darkest blue, up to the red is plus 25 C. And the triangles are with charge, and the circles are neutral. So what you see here is when we get charge present, all of the particle formation rates are about the same, independent of temperature, as long as we measure the ULVOC concentrations. The ULVOC yields are by no means the same at different temperatures. And the particle formation rates are between 1 and 10 particles per cubic centimeter, and depending roughly quadratically on the ULVOC concentration, meaning that the particle formation rate goes approximately like the ULVOC squared, which is consistent with collisions. If we take away charge, the nucleation rate will drop by up to 2 orders of magnitude, but it's also quite a bit more variable, which is actually interesting information that I'll give you just a hint of understanding. But the presence of charge definitely stabilizes these clusters, and it basically enables organic compounds of somewhat higher volatility to participate, and so it accelerates the nucleation rate. So that roughly is what we see. And further, if we look at different terpenoids now, but base the particle formation rates we see on the measured ultra-low volatility organic carbon compounds, we see consistency again. So the same basic figure here, but these are now compounds produced by oxidizing alpha pinene in green, but then oxidizing alpha pinene in the presence of isoprene in the blue, in the cyan, or adding in some beta caryophyllene, a sesquiterpene, and also oxidizing this 3-terpenoid mixture. And we see a very consistent particle formation rate when we measure the ultra-low volatility organic carbons compounds, the dozens of them that are produced. And this is some work that was published by Lib and Dada just last year in Science Advances. The trick is the yields of those ultra-low volatility organic carbons are very different in these different systems. And I want to give you just a hint as to why, and then I will stop. I don't have time to talk about growth, unfortunately, because of reasons. So let's go. We're working on understanding those nucleation rates within the volatility basis set, but I don't really quite have time for that. I'm going to stop with this and one more slide. I think we'll just stop here. So let me back up a little bit. When we model the production of that tail of products into the ultra-low volatility organic carbon range, and make reasonable assumptions about the stabilizing properties of the presence of charge, we wind up with predicted nucleation rates versus ULVOCs. It looks something like this, where the green circles are neutrals, the red squares are the ion-induced nucleation component of this, where with ion-induced nucleation, you can't nucleate any faster than you're making ions. That's what we call Q, or the ion pair formation limit. And so that's this red that becomes asymptotic to the ion pair formation limit at high concentrations. And then the sum of those in magenta is the overall rate at which particles are formed in the presence of the pions or cosmic rays or anything that might make charge. And And we're basically at the point where we can pretty well understand that nucleation rate as a function of these ultra low volatility organic carbon concentrations. And now what we're working on is modeling the actual yields of those ULVOCs and the rest of the products as temperature changes in this space. So the left-hand column is what we actually observe. Red is the highest temperature, plus 25. Blue is the lowest temperature, minus 50 C. And importantly, this is the volatility at that temperature. So the compounds at minus 50 C that are in this ULVOC range are much, 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 much less oxidized than the compounds at plus 25 C because of Clausius-Clapeyron. So what's going on here? And then the right-hand column is what we model with the literally today's volatility basis set model, which is getting there. It isn't quite right, but it's in a lot of cases it is we've got it pretty well matched at higher temperatures, and there's some issues at lower temperature that we understand that we're still working to resolve. But we're doing a very good job of reproducing this distribution of products in this full range. And what's going on is that as it gets colder, that hydrogen atom transfer associated with this autooxidation process gets slower. It's a hydrogen atom transfer. It's got a high activation energy. So that slows down, and we terminate the peroxy radical chemistry earlier in the sequence. So they're less functionalized, they have less polarity, there's sort of intrinsic volatility, their 300 Kelvin volatility is higher. However, when you make it colder, they stick better. Their actual vapor pressure goes down. And those two things roughly cancel each other out. And because of that, what we see is the production of the ultra low volatility organic carbon stays roughly constant, even as as temperature changes. The other thing that happens, and the other consequence of this critical step of the peroxy radicals reacting with each other to make these covalently bound association products, is if we start to add in different hydrocarbons, like peroxy radicals from isoprene, well, then we get a C15 covalently bound product instead of a C20 product. That is a higher vapor pressure, and the nucleation rates go down. The yields of the ultra low volatility organics go down, and the nucleation rate also goes down correspondingly. If we put in a C15 sesquiterpene, then the carbon number of the products is greater, the volatility is lower, and that's kind of an antidote to the suppression of nucleation by isoprene. So this new chemistry means that the oxidation sequences of all of these hydrocarbons are completely coupled to each other when it comes to particle formation. It's not just coupling by their mutual influence on the on HO2 concentrations and on NO. They're coupled directly. And that means we need to understand the kinetics and yields of both the autooxidation process and these peroxy radical formation reactions, which form, I mean, it's kind of horrifying. It's kind of wonderful as well, because there's hundreds of these peroxy radicals out there, and it's a matrix, right? It's quadratic. So with 100 peroxy radicals, I've got 10,000 reactions that I care about. So what we need is a lot more laboratory kinetics in addition to a lot more understanding of these reactions, which makes me very happy. So I apologize for the technical problems. I went a little bit long there, but I will now stop, and let me get to the last bit here. Either between losing the sound and the pictures, you've completely just blissed out like Lulu on the left, or somehow or another I have you remarkably focused. You may jump in here anyway, like this little terrier, and you actually have questions, and I would be super happy to try to answer them. So thanks very much.
Thanks, Neil. What a way to stick the landing with these puppy pics and cat pics.
Oh, yeah,
so if anyone has any questions, now is the time. You can raise your hand, you can unmute yourself. You could put it in the chat and I could read it out loud.
Dance is accepted.
Oh, go ahead, Russ.
Uh-oh.
There we go. Great stuff, Neil. Fun. I couldn't help but thinking, as you go through all these steps and the oxidation, the species become more oxidized. Both their solubility and hydroscopicity change.
Yeah.
So these are not rare species in the atmosphere. I mean, they're pretty pervasive, and so they're going to get picked up in deep convective clouds, and and at least some of them are going to have a lifetime that'll get them to the upper trope. And so, have you thought about how, will they behave as CCN or ice nuclei? Because you might be filling the upper trope lower strat. Maybe that's why you're looking at -50. Maybe you're already thinking about
Maybe. We don't just go to -50 because we like to wear very heavy clothing. Yeah. Yeah, I will say that there's some very interesting results that are going to emerge from the Cafe Brazil Halo mission, that have had some companion experiments at cloud. I won't say anything more about that because those are but there's so yes, the simple
Sorry.
answer is now one thing about these though is that none of these things have any right to be in the gas phase.
Mhm.
None of the things, I mean, everything kind of that I was talking about today, all of the great thing with the Europeans is they try to pronounce the acronyms. And I've got LVOCs as in ELVOCs, and I've got LVOCs as in LVOCs, and I've completely confounded them. And so that, and making the ULVOCs is also great because it's more or less unpronounceable. But all of those classes are, the LVOCs have a little tiny vapor pressure that I care about a little bit, but really their gamma to particles is close to 1. And so the lifetime of all of these things is the condensation sink. So yeah, they're water soluble. And so if you're in a situation where the condensation sink is water droplets, they're going to go in. And I mean, they're not, I don't even really care about their solubility in a sense. They're going to stick to the particles, stick to the water, and stay on the surface if their Henry's law coefficient isn't right. But they have no discernible vapor pressure. So that's one of the interesting things there is you kind of have to make them, it's a dish that you don't sit around and put in the oven. You got to eat it when it comes off the flame. So it's getting the precursors into the upper troposphere, I think, more, and doing the chemistry there more than carrying these species around. They don't really transport well.
Right, but the precursors do.
Yeah, for sure.
So
I mean, that's
okay.
Go ahead. Yep.
Oh, I just say I didn't mean to try to get you to talk about your next Nature article, but this is a big part of the natural background that probably by adding NOx we've perturbed it. So good
Yes.
stuff.
Yeah, so that and you've hit on another thing, which is obviously the NO. That NO is a somewhat more subtle effect than it appears at first blush, which is so obviously NO suppresses RO2, right? So if you need to spend time, especially when it's cold, slowly methodically working your way down that auto oxidation sequence, and NO shows up and shortens the RO2 lifetime, that'll shut you down. Right, so that does slow things down. However, we've understood the isomerization of alkoxy radicals, of RO radicals, much longer than the autooxidation of RO2. It's much easier, and so sometimes just a little dab of NO is perfect because you're in a situation where most of the RO2s are still reacting with something other than NO, but the NO plus RO2 getting you to an RO radical, which then isomerizes, can act as a kind of a catalyst for autooxidation. So under some circumstances, very low but non-zero NO is actually a very useful thing in this game.
Yeah, Cool. Well, thank you.
All right.
Yeah, there's more than a soupçon of NO in the upper trope usually. So
Yes, indeed. There sure is. I see a Salowich hand up.
yeah, go Ross.
Hey. Hi, Neil. It's great to see you. Too bad it's only over the screen, but
Yeah.
hopefully we'll see each other in person sometime in the not too distant future. Um, I have a question from 10,000 feet, because that's sort of where I sit in relation to, your fantastic seminar. So at the beginning of your seminar, you talked about the great need, the great motivation of this type of research to try to understand radiative forcing in climate due to aerosols. So that's kind of the beginning of the question. And, throughout the IPCC reports and the literature, particularly the Smith and Bond paper, there's an assertion that RF, radiative forcing climate due to aerosols, is essentially going to be close to zero by end of century because of public health concerns and awesome figures you showed with the EPI results, which I had not seen before. That was great. So my question to you after this long dialogue is, how off might that be, given the preponderance of organic sources, greening of the biosphere, whatever. Have you thought about that? I mean, do we really have to pause and think whether it's nature or humans that we still might be contending with some RF due to aerosols at the end of the century? Because generally in IPCC, they don't.
Yep. And so I alluded to that as well, in the sense that the it is often, in my opinion, as you just said, more or less implicitly or explicitly assumed that we just kind of roll back to the pre-industrial in terms of aerosols, and I'm way overstating it. But as we decarbonize and as we address the urgent the health needs, but health effects, yes, we care about ultrafine particles. Their deposition fraction is way higher than accumulation mode particles. Accumulation mode particles are like the Goldilocks of particles. They have very low mobility, but they're small enough. They're the ones that are super hard to get with a mask, right? They have low mobility, but they're small enough that they have very little inertia, and so they tend to hang out for a very long time in the atmosphere. And they also, if you breathe in, you breathe most of them right back out. So the ultrafines, however, are much jitterier, and so if you breathe them in, they all deposit. But there's no mass. So when we look at the health effect association, still, I mean, actually anywhere, World Health Organization or the EPA, the standard is based on just the total mass of stuff smaller than 2.5 microns. Doesn't matter what the composition is,
Yep.
and it's just the mass.
Yep.
But it's a dose response, so we're sure that the composition actually does matter. But still, even accounting for that, it's more than likely it's dosage, and the dosage is somewhat moderated by the deposition fraction, by actually getting the particles to stick inside your lungs. So the health effects are associated with mass. The climate effects are number. And so it just isn't obvious that the number distribution is going to sort of behave in a very predictable way as so we're probably not going to reduce ammonia very much. And I didn't
feed people, yep.
Speaking of the upper trope, so
Yep.
Russ as well, this is a figure we published. I don't do everything with organics. This is nucleation rate versus ammonia under conditions of the Asian monsoon, basically. And one thing we found was that you get cold enough and ammonium nitrate is non-volatile. And so ammonium nitrate starts to look like ammonium sulfate from the point of view of particles. And so the blue curve, excuse me, is the nucleation rate of a mixed system of sulfuric acid, ammonia, and nitric acid. And we see 100 times more particles being formed under those conditions than the kind of traditional red curve, which is good old ammonia sulfuric acid nucleation, which is the sort of the state of the art for a lot of models. So we make way more particles out of ammonium nitrate. It's also consistent with ATOM observations, etc. So and how you get that ammonia into the upper troposphere is a neat little trick. That what we presented in the paper that this figure is out of was that basically freeze pump thaw. So when convective systems entrain ammonia and freeze, there's enough of a vapor pressure of ammonia over those frozen particles that you get some ammonia off, and when they're detrained, you get some ammonia out of that. And ammonia is observed in the Asian monsoon upper troposphere, and so that leads to particle formation. And there's no projection I'm aware of that shows significant decreases in ammonia. So on the inorganic side, there's mechanisms for generating particles. On the organic side, as we reduce NOx, all this autooxidation chemistry I'm talking about is going to be, if anything, more abundant. And so once again, it's not obvious that the particle number is going down very fast.
It'd be nice to have IPCC do a little bit of chemistry on the methane and nitrous oxide projections. They never have nitrous oxide turning over. And of course, for those who don't know, that's connected to the reduced nitrogen through fertilizer use. Hey, I have a completely different question, but I've been at times accused of monopolizing the questions. So I'm going to pause and
I've been
only ask
accused of
my other
monopolizing
question.
the answers, so okay. I'll wait for the other question with
Are there
bated
other
breath.
questions?
We lost some people at the turn of the hour.
Okay. Well, I'm gonna let me just get this one because we're recording. So I'm gonna take the bait that Neil put forth, or the opportunity. At the very beginning of his talk, he talked about the new policies in place to scrub marine emissions. And for those who don't know, which is probably nobody hearing my voice right now, 2023 was record warmth, and there is some thought that maybe the scrubbing of aerosol precursors from ships throughout the world is a big factor in that. So with that as the question, and Neil, you said you would invite, you had your meeting, there's a lot of discussion, and you would invite a question on this. So why don't you take that and tell us what you would like about marine emissions and their climate effect.
I won't necessarily. Oh, you mean tell me what I would like as in speak about what I would like to speak about, not what I would like
but
to
do you
see
think,
as policy?
Well, do you think
okay.
do you think the new scrubbing of I'm using my I forget the bunker fuel. Do you think the new bunker fuel policy is really being seen in the 2023 record warmth?
I don't quite have the 10 to 30,000 feet to say that I have an informed opinion on whether we see an unmasking. So I always, by the way, that's a term I insist on, that aerosols mask long-lived climate forcing. They don't offset it. They don't. I mean, because you got to continually emit them, and they tend to kill people. There's not a lot of people breathing in the marine atmosphere, though there are some. And so when we look at the health effects of emissions, it is true that if you're just an economist and you're just adding up health effects from the increased background concentrations, population matters. And so the emissions in urban areas tend to get weighted much more in terms of health damages than emissions in the Central Pacific Ocean. So that's where there is some questioning of whether getting rid of stuff that tends to make particles in areas where there aren't so very many people breathing is fully prudent policy.
So we may have been marine cloud brightening all along.
We may have been marine. I mean, obviously we were doing some, because you can find those ships from space pictures all over the place, right? So there's the question of how much.
Yep.
It doesn't do you much good if you brighten the third deck down in a complex cloud layer. So there are all sorts of things about surface marine brightening that are, as an active effort, are challenging, but as kind of a, there certainly are lots of ship tracks, and I don't know whether quantitatively the numbers add up there, but it's certainly something to that it's interesting to think about. And again, to me, I think it's super important that we understand that making particles is way more than just some sulfuric acid, even though the bunker fuel case, it really is sulfuric acid. That there's the organics that come from us, that come from natural systems that mix with nitrogen oxides that come from us, different organics interacting with each other. I didn't even get close to talking about iodine. And all of these, there's a richness to particle formation chemistry, some of which was going on just fine before humans ever showed up, some of which we've dramatically changed over the past couple hundred years. And it just isn't obvious that reducing the cleaning air from the point of view of air quality will necessarily reduce particle numbers. It might. That might be serendipity, but it's actually not at all hard to construct systems in the laboratory where you reduce the particle mass, which, remember, that's lowering the condensation sink dramatically, and the aerosol number goes up. That's not hard to do.
Yep.
In fact, it's fairly easy to do. And so I don't take it as a given that we're just walking back towards zero.
Thanks, Neil.
Yeah, thank you.
Okay, we're quite a bit over, which is totally fine. That's why we have recordings and virtual sessions. So as long as it's you guys have time, you could talk forever. But I'm gonna close the session.
That's true. All right.
I'm just gonna close the seminar. But I'll leave the Zoom open if you want to keep chatting. This is recorded, but I'll just stop the recording. So
right.
thank you for attending our seminar. Thank you for giving this great talk, Neil. It's always nice to hear from other ESSEC colleagues, or not our colleagues of my ESSEC colleagues. It's a good connection point. And then to everyone else, we will be continuing our seminar series next week. So thank you.
Thank you.
Good luck to methane sat. It launches in a few hours.
Oh, good luck.